Well, hello everyone, and welcome to yet another problem from Geeks for Geeks. So, here we are asked to count pairs whose sum is lesser than target. Now, within this problem, we are given an array as usual, and we are given a target. We need to find the number of pairs occurring within an array whose sum is strictly less than the target. So, for this target, we have two such pairs. What are those? Are 2, 3, and 2, 5. Well, a simple solution for this one can think of is, hey, why don't we go ahead, use two pointers and make the solution in O of n square with using I and j for loops. Two loops, pretty much simple. Yes, we can do that, but can we do better? Can we do it with an O of n solution? The answer comes out yes, but how? You see, within the first problem within the first approach, we were having a fixed value as I, and then we find j, and we adjust j in such a way that if we find a sum of I plus sum of j which is greater than target, we do not no longer need to search, and instead we go ahead next time and do I plus plus, right? Because we need to check within the two for loops solution, can we minimize these two things within one loop and iterate both? What do I mean is, first of all, I was iterating from 0 to n minus 1, and j was also iterating from 0 to n minus 1 respectively. But what if I say you that, hey, let I iterate from 0 to certain point or n minus 1, and j on the other hand iterate from left to right. This would especially occur within a type of array which is sorted. So when the array is sorted in this manner, 2, 3, 5, and 7, let's say I have this I or left pointer here over here, right pointer over 7, and I need to check whether this would go ahead and make a perfect solution or not. It says no. So what do? We need to check that, hey, because the sum of this is 7 plus 2 is 9, which is greater than target, which means greater than target, which means we need to lesser down, lesser. So let's remove the lesser quantity, which is r, because it is sorted, right? And r denotes the far more greater quantity. So lessening the r would give us 2 and 5, and we know that, hey, if I am going ahead and for this sum is equal to 7, which is lesser than target, then it's good, increase count. But wait a second, if we go ahead and think for a while, if I do r minus minus, again it will satisfy till the point r is not equal to l, I mean. So can I do a quick shortcut over here? Because when I say that 2 and 5 satisfies, doing r minus minus would give rise to 2 and 3, which also satisfies. So can I say that r minus l, all these ranges satisfy the condition, satisfy the count or the condition? So increase count plus equals r minus l. Why can't I do this? Obviously I can, because keeping this into my mind, 0, 1, 2, and 3, from 2 minus 1 I get 2 minus 0, I get 2. And once I do this, I no longer need to check for L. No longer check for L. So update L. Cool. What I'm going to do is I'm going ahead with this hypothesis within the code, and this I'll do until we have our left and right pointers satisfied. So what do I mean by this is, while left and right, there's something between left and right, and that means left is lesser than right. And obviously for this I need two things, which is left pointer initially 0, right pointer initially a dot length -1 because index, and count which is initially 0. And I need to check these two conditions. So let's bring it down, these two conditions. Yeah. So first thing is, what I wanted to do is check if, figure out the sum. Obviously sum is equal to a of L plus a of R, and if this sum is greater than target, we need to lesser it. How do we lesser it? R minus minus, the one which we have seen earlier, like this. Else we have a very good case that, hey, this satisfies our condition. It means increase the count. So while going forward, I'm increasing the count. Let me full screen this one. I'm increasing the count to count plus equals to R minus L. This makes sense as we have derived it over here. R minus L satisfy the condition. So this will keep on running, and I'll no longer need to stick with L, and hence I'll update L. So L has been updated to L++, and ultimately I return the count because both the pointers are merging into each other, which would meanwhile terminate this loop. And then once the loop is terminated, we return the count. So this looks good to me. Let's submit this one. Let's come out of the full screen. Okay, there's something issue within this. Okay, we need to have a strictly lesser than now, right? So I'll just use greater than or equal to, because it seems that 3 has been counted with 3 again. Okay, 4 5 2 3 4 1. Am I sorting the arrays? No, I'm not sorting the arrays. So I need to go ahead, arrays dot sort it first of all a, and then I need to go ahead. So I've sorted this, count is ready, L and R are at its position initially. So we have calculated sums. Okay, prior to try running, it has submitted. Well, it seems that our code has passed the test cases, and this was one of the problems from the topic of two pointers. It's very interesting topic, basic yet very subtle to ignore. This could have been solved with help of binary search, but that went ahead within the complexity of n log n. Having said that, this algorithm also has a complexity of n log n because we use sorting algorithm. And if this array was sorted, this would run in O of n, but if you want still more ease, then we can go ahead and use binary search upon this in order to check one and find out one. So this was all about it. For more such two pointer and binary search algorithms, follow my channel, and I'll see you in the next one.